My name is Catherine Canatella, and this is my Motion of Falling Objects lab report. I observed a filled water bottle which fell quickly and a koozie which fell slowly. The main result was that air resistance causes objects to fall at different speeds. The main objectives of this experiment were to compare velocities of falling objects, find terminal velocities, and establish a relationship between air resistance and weight ratio. First, we will see in Tracker how the filled water bottle falls quickly. I set the axis so the bottle falls in the negative y direction. I set the calibration stick for the length scale in my video as 0.185 meters, which is the length of my bottle. My time interval starts right as I drop the bottle to right before it hits the floor, which is a total time of 0.4 seconds. I set the center of mass equal to the center of the water bottle. This second video, we will see the koozie fall slowly to the ground. I again set the axis so the koozie falls in the negative y direction, and I set my calibration stick to the length of the koozie, which is 0.26 meters. I then tracked the koozie as I dropped it until right before it hits the floor, which made my delta t 0.734 seconds. I set the center of the mass at the center of the koozie. I then created computational models for both the slow and fast-falling object. For each object, I did one model with drag and gravity acting on the object, and one model with only gravity acting on the object. As you can see, I used Newton's second law to perform the simulation. This is the heavy object, which is the fast-falling object, moving with only gravity acting on the object. As you can see, I set Fnet equal to only Fgrav, and then use Newton's second law to predict the terminal velocity. My delta t is 0.033 as seen in Tracker, and my ball mass is 0.142 as seen in Tracker. Now I'm going to run the simulation. As you can see, the ball fell with gravity acting as the only force on it. Now I'm going to show you my light ball model. As you can see, this is my light object. It has a mass of 0.002, and because of that mass it fell slower than the other object. My delta t is 0.033 as seen in Tracker. Again, I use Newton's second law, setting Fnet only equal to Fgrav. I'm going to run this simulation. And the koozie fell with only gravity acting on it. These next two models are for both the fast-falling object and the slow-falling object. The first one is for the fast-falling object. As you can see, Fnet is now equal to Fdrag plus the force of gravity. My ball mass for my fast-moving object is still 0.142. My delta t is still 0.033 as seen in Tracker. And now I'm going to run the simulation. As you can see, the ball now falls with gravity and Fdrag acting on it. Now this is my slow falling object. As you can see, once again, I used Newton's second law and I set Fnet equal to Fgrav plus Fdrag. My mass of the ball is still 0.002. And my delta t is still 0.033 as seen in Tracker. I'm now going to run the simulation. As you can see, once again, the ball falls with both Fgrav and Fdrag acting on it. I then graphed all my data in Excel. As you can see, this is the graph for the slow falling object and this is the graph for the fast falling object. The blue diamonds are the experimental data collected from Tracker, while the green triangles are the computational model with both the force of gravity and the drag force, and the red squares is the computational model with only the force of gravity acting on it. As you can see in both models, the computational model with both Fdrag and Fgrav more accurately predict the terminal velocity for each case. What does this mean? For the object that drops slowly, examine the velocity versus time predicted by your models with and without drag. Which models, if any, predict a terminal velocity? Discuss briefly. First, we use the computational model to predict F drag. We set F drag equal to negative BV. This means that F drag is proportional to the negative velocity. We also use Newton's second law to predict F drag. As you can see in the graph, this drag force causes the curve to flatten out. Eventually, F net will equal 0 because F drag keeps increasing. When these forces do equal each other, the pulses and poles will be the same and the terminal velocity will be reached. What if? For the object that drops slowly, use your models to examine the object's velocity as a function of time. In the case where the object is thrown downward initially, in this case, does the object reach a terminal velocity? Compare the terminal velocities, if any, in this case with the case where the object is dropped from rest. If the object is dropped with initial velocity in the negative y direction, this causes the object to reach its terminal velocity much quicker, because the force of drag is proportional to negative velocity, and if the velocity is in the negative y direction, the negative velocity is no longer starting out at 0. Instead, it's starting out as a real number, such as 2, 3, or 4. But now, if the object is dropped with initial velocity in the negative y direction, and drag is not taken into account in the force acting on the object, the velocity just keeps increasing in the negative y direction, and a terminal velocity is never reached.